Implementation of Advanced Reusable Rocket Technology by Q2 2024. Executive Summary. The aerospace industry is on the cusp of a transformative leap with the upcoming implementation of advanced reusable rocket technology expected to enhance launch efficiency by up to 60% by the second quarter of 2024. This ambitious initiative is backed by a substantial investment of $15 million, which will be strategically distributed across 4 pivotal development phases. Development Phases Overview. The project is structured into 4 key phases. 1. Phase 1, Research and Development R&D. This foundational phase focuses on the innovation and refinement of rocket designs. Emphasis will be on developing advanced materials and propulsion systems capable of enduring the rigors associated with repeated launches. 2. Phase 2, Prototype Construction. Following the successful R&D, this phase will involve the construction of prototypes. These prototypes will be critical for testing new technologies under real-world conditions, allowing for the identification of improvements and resolution of any unexpected challenges. 3. Phase 3, Testing and Validation. Extensive testing will be conducted to validate the prototype's performance, safety, and reliability. This is a crucial step in ensuring compliance with regulatory standards and operational requirements, ultimately paving the way for market readiness. 4. Phase 4, Full-Scale Production. Upon successful validation of the prototypes, the project will transition into full-scale production, enabling the provision of regular launch services utilizing the new reusable rocket technology. Key highlights. Cost reduction. The initiative aims to significantly lower the costs associated with space launches by introducing reusable rockets. This addresses one of the major barriers to accessing space. Sustainability focus. The technology contributes to environmental sustainability by reducing waste associated with one-time use rockets, thereby minimizing the ecological footprint of space missions. Context and global significance. The push for advanced reusable rocket technology is particularly significant in the current context of escalating global space competition. Countries like China are ramping up investments in their space capabilities, highlighting the urgent need for innovation in launch technologies to meet the increasing demand for satellite deployments and broader space exploration initiatives. Divergent perspectives. While there is consensus among various sources regarding the anticipated improvements in launch efficiency, they diverge on the specifics of the technologies being developed. Some reports emphasize advances in propulsion systems, while others focus on breakthroughs in materials science that enhance durability and performance. Timeline of events. 2023, initial funding and kickoff of the project, including early discussions on technology specifications and potential partnerships. Q1 2024, completion of the R&D phase. Setting the stage for prototype design and engineering. Q2 2024, expected public unveiling of prototypes and the start of rigorous testing protocols. Use cases and applications. The implications of this technology extend beyond traditional space launches. Potential applications include satellite deployment. Enhanced launch capabilities will allow for more efficient and frequent satellite deployments. Interplanetary missions. The technology could facilitate ambitious interplanetary exploration missions, advancing scientific knowledge and technological prowess. Commercial ventures. Opportunities in space tourism and commercial satellite services could become viable, democratizing access to space for private entities and individuals. Conclusion. The development and impending implementation of advanced reusable rocket technology represent a critical advancement in the aerospace sector. With a structured approach to development and a considerable financial investment, this initiative is poised to enhance both efficiency and sustainability in space exploration. The project not only aims to revolutionize launch practices but also addresses the growing need for innovative solutions in an increasingly competitive global landscape. The commitment to this endeavor underscores the importance of advancing aerospace technologies to ensure continued progress in exploration and utilization of space resources. The implementation of advanced reusable rocket technology by Q2 2024 presents various counterintuitive insights and implications for the aerospace sector, particularly concerning cost efficiency and sustainability. 1. Investment versus launch efficiency. The initial investment of $15 million across 4 development phases aims to enhance launch efficiency by 60%. Normally, one might expect significantly higher investments to yield such substantial efficiency gains, suggesting that innovation in design and materials could be more impactful than previously understood. It challenges the notion that more capital directly correlates with better technological outcomes. 2. Sustainability versus profitability. While reusable rockets are touted for their environmental benefits, the underlying economic incentive is often overlooked. The expectation is that making rockets reusable will reduce costs significantly, thus making space more accessible. However, the counterintuitive aspect lies in the fact that the same technology may also lead to increased frequency of launches, which could paradoxically heighten the overall environmental impact, something that might not be immediately apparent when considering the sustainability aspect alone. 3. Technological development phases. The structured 4-phase plan R&D, prototype construction, testing, and full-scale production suggests a linear progression toward innovation. This approach can be misleading. Real-world technological development often involves setbacks, iterative improvements, and unexpected breakthroughs that do not fit neatly into predefined phases. The assumption that each phase will culminate in a clear advancement may overlook the complexities and nonlinear nature of technological evolution. For competition and innovation, the focus on reusable rocket technology is partly a response to global space competition, particularly with countries like China ramping up their capabilities. This might imply that innovation is primarily driven by competitive pressures. However, the counterintuitive insight here is that collaboration and shared knowledge across borders could actually accelerate advancements in technology, suggesting that competition may not always be the best catalyst for innovation. 5. Market accessibility versus quality control. The initiative aims to democratize access to space by reducing launch costs. However, the influx of more frequent launches could lead to quality control issues as companies rush to meet demand. This contradicts the expectation that increased access would result in better quality and reliability in space missions. 6. Regulatory compliance. The project's success hinges on meeting regulatory standards during testing and validation. Yet regulatory frameworks often lag behind technological advancements, which can create a bottleneck for innovation. This suggests that while the timeline for development appears streamlined, the unpredictability of regulatory responses could significantly alter the pace and feasibility of the project. 7. Broader applications. The technology is expected to extend beyond traditional space launches to areas like satellite deployment and space tourism, which could lead to unexpected market dynamics. For instance, the potential boom in space tourism could divert resources and attention from scientific exploration and satellite technologies, revealing a counterintuitive trade-off in prioritization. 8. Environmental perception. The narrative around reusable rockets emphasizes their environmental benefits. Yet the actual reduction in carbon footprint may not be as significant as suggested if launch frequencies increase. This juxtaposition highlights the complexity of environmental metrics in the aerospace sector, where intentions and outcomes may diverge. These counterintuitive insights challenge conventional wisdom about technological development, market dynamics, and environmental implications, emphasizing the need for a nuanced understanding of the impacts of advancements in reusable rocket technology. The report on the implementation of advanced reusable rocket technology by Q2 2024 is rich with significant insights that may be overlooked by many readers. Here I will identify and elaborate on some of these key components and their implications. 1. Investment breakdown and its implications. While the report mentions a $15 million investment across 4 development phases, it does not provide a detailed breakdown of how this funding will be allocated within each phase. Understanding the specific allocations can shed light on the priorities of the project, such as whether more resources are directed towards R&D, prototype construction, or testing. Such insights could indicate the confidence of investors in the technology's feasibility and the anticipated challenges. Moreover, the level of investment may influence partnerships with other stakeholders, including government agencies or private firms, which could further accelerate development timelines or enhance technological capabilities. 2. Sustainability and environmental impact. The report states that reusable rockets contribute to reducing waste and minimizing the environmental impact of space missions. However, the specifics of how these improvements will be quantified or regulated are not discussed. This is significant because as the space sector grows, so does scrutiny over its environmental footprint. Highlighting the sustainability measures, such as the type of fuels used, emissions during launches, and life cycle analysis of the rockets, could strengthen the case for this technology in an increasingly eco-conscious world. Furthermore, the push for sustainability aligns with global efforts to mitigate climate change, which could attract positive public sentiment and regulatory support. 3. Competitive landscape. The report briefly mentions the global space competition, particularly in relation to countries like China ramping up investments in space capabilities. However, it does not delve into the specific competitive advantages or potential partnerships that could arise from this initiative. For example, identifying how this technology positions the company against competitors or how it could foster international collaborations could provide a clearer picture of its strategic significance. Understanding the competitive landscape is crucial for stakeholders to assess potential market share and growth opportunities. 4. Regulatory and safety standards. The third phase, testing and validation, is critical for ensuring that the technology meets regulatory standards. However, the report lacks detail on what specific regulations are anticipated and how the project plans to navigate them. This is significant because compliance with safety and regulatory standards can be a major hurdle in aerospace development. Clarifying how the project will engage with regulatory bodies such as NASA or the Federal Aviation Administration (FAA) and what safety protocols will be implemented could provide assurance to investors and stakeholders about the project's viability. 5. Timeline and milestones. While the report outlines a timeline of events leading up to Q2 2024, it does not specify the key milestones that will be monitored throughout the development phases. Establishing clear milestones is essential for tracking progress and ensuring accountability. This could involve interim assessments of the prototype's specific performance targets during testing, or regulatory approvals needed at each stage. Detailing these milestones would enable stakeholders to gauge the project's trajectory and make informed decisions about future investments or collaborations. 6. Potential applications beyond traditional launches. The report mentions that applications for this technology extend beyond traditional space launches, including satellite deployment and space tourism. However, further exploration of these potential markets could reveal valuable opportunities. For instance, understanding how this technology could facilitate interplanetary missions or support commercial ventures could attract a wider range of investors and partners. Additionally, discussing how advancements in reusable rocket technology could lower costs for various sectors such as telecommunications or research institutions would underscore its broad economic impact. 7. Public perception and engagement. The summary does not address how public perception and engagement will be managed throughout the development and deployment of this technology. As public interest in space exploration grows, so does scrutiny. Effective communication strategies that highlight the benefits of reusable rocket technology and address public concerns such as safety, environmental impact, and technological reliability could enhance public support and foster a more favorable environment for space initiatives. Conclusion. In conclusion, while the report provides a comprehensive overview of the implementation of advanced reusable rocket technology, several critical components may be overlooked by readers. A deeper examination of the investment breakdown, sustainability measures, competitive landscape, regulatory standards, timelines, potential applications, and public engagement strategies could significantly enhance understanding of the technology's implications and its transformative potential within the aerospace sector. Addressing these areas not only underscores the project's significance but also prepares stakeholders for the opportunities and challenges that lie ahead in this rapidly evolving field. 1. Investment and economic impact. The $15 million investment in the Advanced Reusable Rocket Technology Initiative underscores the substantial economic implications of this project. By enhancing launch efficiency by 60%, this technology could significantly lower the costs associated with space launches, thereby democratizing access to space. This reduction in costs is crucial for both governmental and private sector entities promoting growth in space-related industries such as satellite deployment, space tourism, and interplanetary missions. The economic ripple effects could stimulate job creation, technological advancement, and new markets within the aerospace sector. 2. Development phases and innovation. The project's structured approach through 4 distinct development phases: research and development, prototype construction, testing and validation, and full-scale production, highlights the importance of systematic innovation in aerospace technology. Each phase is designed to build upon the successes and lessons learned from previous stages, ensuring a rigorous and methodical path to market readiness. This phased development not only mitigates risks associated with technological failures but also allows for iterative improvements, fostering a culture of continuous innovation within the aerospace industry. 3. Sustainability and environmental considerations. The push for reusable rocket technology aligns with global sustainability efforts as it aims to minimize waste and reduce the environmental impact of space missions. By making rockets reusable, the initiative addresses one of the critical environmental challenges posed by traditional single-use launch vehicles. This focus on sustainability is increasingly becoming a priority for both governmental and private space endeavors, reflecting a broader industry trend towards responsible and eco-friendly practices. As space exploration expands, the integration of sustainable technologies will be vital in ensuring the long-term viability of space activities. 4. Global competition and strategic positioning. The initiative is set against the backdrop of intensifying global competition in the space sector, particularly with nations like China ramping up their investments in space capabilities. As countries strive to establish themselves as leaders in space exploration and technology, advancements in launch technologies become essential for maintaining competitive advantage. By investing in reusable rocket technology, stakeholders position themselves strategically within the rapidly evolving aerospace landscape. This initiative not only enhances national capabilities but also contributes to a broader dialogue on innovation, collaboration, and competition in the global space arena. 1. SpaceX Falcon 9 reusable rockets. 2010-present. SpaceX revolutionized the aerospace industry with its Falcon 9 rocket, the first orbital-class rocket capable of reflight. The Falcon 9's first stage can land back on Earth after launch, allowing for significant cost reductions in space travel. Following numerous successful flights and landings, SpaceX has demonstrated that reusable rockets can dramatically enhance launch frequency and lower costs, achieving an over 50% reduction in launch costs compared to traditional expendable rockets. 2. NASA's Space Shuttle Program. 1981 to 2011. The Space Shuttle was a reusable spacecraft designed for human spaceflight missions. The program aimed to provide a reliable way to transport astronauts and cargo to and from low Earth orbit. With 5 operational orbiters, the shuttle completed 135 missions, achieving a level of reusability that allowed for a significant reduction in operational costs per flight when compared to single-use spacecraft. Despite its eventual retirement due to safety concerns and high operational costs, the shuttle program laid the groundwork for the future of reusable spaceflight. 3. Blue Origin's New Shepard. 2015-present. Blue Origin's New Shepard is a suborbital rocket designed for space tourism and research. The vehicle is fully reusable with both the rocket and its capsule capable of returning to Earth after flight. Following multiple successful test flights, New Shepard exemplifies the potential of reusable rocket technology to facilitate regular access to space. The program emphasizes safety and cost-effectiveness, catering to both commercial space tourism and scientific missions, showcasing the viability of reusability in the emerging space tourism industry. Future outlook, predictions for advanced reusable rocket technology. As the implementation of advanced reusable rocket technology approaches its projected timeline for Q2 2024, several key trends and predictions emerge regarding its impact on the aerospace industry and beyond. This initiative is not only about enhancing launch efficiency but also reshaping the economic, environmental, and strategic landscape of space exploration. 1. Significant cost reductions in space access. With a targeted 60% increase in launch efficiency, the economic implications are profound. This technology could dramatically lower the cost per launch, making space more accessible for commercial ventures, research institutions, and even educational programs. By 2025, we can expect new players to enter the market, leading to an increase in satellite deployments and experiments in low Earth orbit (LEO). 2. Acceleration of satellite deployment. The anticipated cost reductions will catalyze a surge in satellite launches, particularly for small satellites and constellations aimed at applications like Earth observation, telecommunications, and global internet coverage. By 2025, we could see a significant rise in the number of operational satellites, with companies and governments leveraging these platforms for data analytics and services. 3. Enhanced sustainability practices. The emphasis on reusability aligns with global sustainability goals. As the aerospace industry faces increasing scrutiny regarding its environmental impact, reusable rockets will likely become the standard. The reduction of space debris and a lower carbon footprint from decreased manufacturing and launch emissions will be significant advancements touted by the industry by the end of the decade. 4. Geopolitical implications and space race intensification. Countries like China and the United States are rapidly advancing their space technologies. The successful deployment of reusable rocket technology could intensify the space race as nations strive to maintain or gain leadership in space exploration and satellite deployment. By 2026, we may witness increased military and strategic uses of space, with nations using their capabilities to enhance surveillance, communications, and defense systems. 5. Emergence of new commercial opportunities. As launch costs decrease, new business models will emerge in the commercial space sector. This includes opportunities in space tourism, asteroid mining, and in-orbit manufacturing. By 2027, we could see the launch of the first commercial space hotels or platforms supporting microgravity research, driven by the availability of affordable and reliable launch services. 6. Technological innovations in rocket design. The research and development phase will yield breakthroughs in materials science and propulsion technologies. By 2025, innovations such as advanced composite materials and hybrid propulsion systems could significantly enhance rocket performance and safety, leading to more ambitious missions beyond Earth orbit. 7. Global collaborations and partnerships. The complexity of space missions will necessitate international collaboration. By 2025, expect to see an increase in partnerships between space agencies, private companies, and academic institutions. Collaborative efforts may focus on shared missions to the Moon and Mars, leveraging reusable rocket technology to lower costs and risks associated with these ambitious endeavors. 8. Regulatory and safety framework developments. With the deployment of reusable rockets, regulatory bodies will need to adapt existing frameworks to ensure safety and compliance. By 2024, we may see new guidelines and regulations emerge globally, focusing on launch safety, airspace management, and the environmental impact of rocket launches. 9. Growth of space debris management solutions. As satellite deployments increase, so will the challenge of space debris. By 2026, expect the emergence of innovative solutions for debris tracking and removal, potentially integrating with reusable rocket missions to ensure sustainable use of orbital regions. 10. Long-term vision of interplanetary missions. With advancements in reusable rocket technology by 2030, we may be looking at the feasibility of crewed missions to Mars and beyond. The technology's potential to reduce costs and increase mission frequency will be crucial in supporting long-term human exploration of other planets, paving the way for future colonization efforts. Conclusion: the implementation of advanced reusable rocket technology by Q2 2024 represents a pivotal moment in aerospace history. With substantial investments and a structured development approach, the industry is poised for transformative changes that will affect not only how we access space but also how we utilize it for various applications. The next decade is likely to usher in an era of unprecedented growth and innovation in the space sector, fundamentally altering our relationship with the cosmos.